Hello, and welcome back to Section 3, Part 2 of the Science Resource Guide for Academic Decathlon. Today we're going to be going over water resources. So we're going to first start by looking at the challenges in actually accessing, well, how do we get clean water? So it begins a discussion of the ancient Romans and how they're very famous for two things, aqueducts and roads. And so the actual difficulty in these systems was actually water pollution. So there was these elaborate systems of pipes and transporting water with all these, as you can see, these long distance aqueducts here that just brought water to different places. The problem with these is that water pollution would build up in them. And so ancient Rome, it had a lot of different inputs of water, which was such as waste receptacles and sewers, and a lot of this water was going into the aqueducts and into the pipes and so forth. And so, because they were congested, a lot of these waste receptacles and sewers came. And so, uh, there were local springs and shallow wells that actually gave water to Rome, but these became polluted because it was congested. And so, s- uh, one of the first people to look into this was Sextus Julius Frontinus, who was a water commissioner for Rome, and his writings survived about the Tiber River, which actually, remember, there's the Tiber River runs through Rome, and so he saw that it was not protected and received too much wastewater, and so it was contaminated and couldn't be a water source anymore. And so the Romans would have needed to bring clean water in from farther away. And so this caused the need for aqueducts overall. So they couldn't just use their own sources of water, such as wells or different rivers, such as the Tiber River. And so they had to create aqueducts. And so the first one or the need for them started in 312 BCE. And this was when the first aqueduct was constructed. So 312 BCE. And then some fun facts about some of the aqueducts in the Roman Empire were that they extended more than 60 kilometers, and by 19 BC, there were more than 400 kilometers worth of aqueducts in the Roman Empire. So that doesn't mean one stretch for 400 kilometers. It just means in total, there were about 400 kilometers built. And so not only did they show how we are in current times needing to rely on water transported in long distances, but we can also take a look at Rome to understand their water pollution problems. And so we see that the Roman aqueduct water actually contained too much sediment, which showed that a lot of the basins that they created here, so a lot of the either constructions or digging into the earth, a lot of sediment got into that water when they were trying to send it to different areas. And so, not only this, but they also found aqueducts, archaeologists did, that were made of lead. And so, when water goes through a lead pipe, the lead leaches into the water. And so, there's high lead concentration in the water, at least compared to regular water. And this is actually, there's a hypothesis that says that the Roman Empire had a decline. The aristocracy, the highest social class, seemed to have a decline in Rome because of the impacts that lead poisoning caused inside of the brain. And so I would say right here is also very important. It's saying, well, wine was also stored in lead vessels. They used lead to store wine, and they drank wine a lot, just like water. And so it could have been a more significant factor than water that had to do with lead pipes or lead containers. Frontinus was also, he could have been the first to consider the use of gray water, so wastewater not containing sewage. And so he wanted to use a lot of the gray water for watering gardens and for more dirty uses of the city. So this gray water, it's wastewater still, but it doesn't contain sewage, so it can be used for other things. So so it seems that his quote here is basically explaining that Frontinus wanted to create aqueducts that separated out, or not separated out water, but we create a separate aqueduct to use only for drinking purposes, and then other for this gray water, this wastewater that doesn't contain sewage, for all the worse uses in the city that we can't drink because it's less clean. And it also seems he believed that so old Anio aqueduct. So note Frontinus seemed to suggest things about the old Anio, using it for watering gardens. And then he also believed that if water is further from its source, then it's less wholesome or it's less clean in this case. Now, we're gonna then begin the next section about, okay, well, how is water polluted even in modern day, and how are we able to safeguard that water and keep it protected from any pollutants? Oh, another thing to note is Rome passed a law that said no one with malice shall pollute the waters. And it's very important today, just as it was then. Okay, so next up, we're going to start to talk about environmental and human systems as it relates to water. And so we need to start thinking back to that hydrologic cycle that we talked about in section 2 and how water covers 75% of the Earth's surface. This should be a pretty easy number to remember if you're ever tested on it. And it's actually only a little bit is actually able to be used as drinking water. And so, or even just as water to feed plants and such. So, if we look at all the ocean's water, or all the Earth's water, only 3% is fresh water, and a lot of that is in glaciers and ice caps. So, a little bit more than 1% of all the water is actually potentially able to be used by humans or other animals and such. And then we are going to begin discussing freshwater, even though it only makes up tiny bit, like 1% of all water. So, where do we get our water? Well, a lot of it is contained underground. So, we have lakes, rivers, and reservoirs, which actually supply half of the drinking water. So, even though most of it is contained underground, we get most of our drinking water from above the ground in lakes, rivers, and reservoirs. Now, these only comprise 0.009% of the water on Earth. So that's a really, really small number. There is even less water tied up in the atmosphere, 0.001%, and then even less in organisms, so 0.0001%. So you can remember, well, okay, this is about 0.01 if you round, but just remember it's that 9 really percent of water, and then it gets even smaller to add one more zero in the atmosphere, and then one more zero in organisms. Okay, so then if we take a look at how the different like compartments or these areas of where water is stored, there could be a little more, a little less in each, depending on where water is flowing currently in the hydrologic cycle. But a lot of these show how water is pretty inaccessible in the earth if you think about it from a larger scale. So let's begin to talk about what makes up most of Earth's fresh water, which is underground in not groundwater, in groundwater, yes. Not surface water. Surface water we will talk about later, but groundwater makes up most of it. So aquifers are these little trapped areas of water in the ground, which have like holes in the rock that allow water to sit there. And so this is what groundwater comprises. And it enters here through infiltration of precipitation and discharge of rivers and streams. So I think this chart here is very important here. If we see that it's raining here, precipitation, and it's going into the aquifer here. So the infiltration, so the movement of water through the dirt into the aquifer. And we also have from discharge of rivers and streams. So if we look, it can sometimes flow into, which it doesn't show here, but it can sometimes flow into an aquifer, which actually we see it like right here. Now, if we take a look at how water sits there in the actual aquifer, unless humans disrupt it, there it's usually going to stay indefinitely. So remember that human activity is what removes water from aquifers. Unless it's a tectonic activity, such as like an earthquake, which shifts the aquifer and allows the water to flow due to gravity. Now, there are also some aquifers that actually open up and go straight into the ocean or go into rivers or streams. And we can also drill a hole into it, which this is what a well is. So if you think about, well, how is a well formed? We drill a hole into an aquifer that allows us to access that water down below where we previously wouldn't have been able to access it. And so this is a lot like drilling into an oil reserve, and then we pump the water out. And so usually basic aquifers is made of porous rock like sandstone or other consolidated sediments and then covered by soil. So we have like this rock that has kind of has a lot of holes and water flows through it, and then soil's just on top of it. So that's what the most basic aquifer is. And so this is called an unconfined aquifer because it's not constrained by any confining rock. So unconfined, it's not confined by any rock. And so then we have this idea that um, the part of the aquifer that has water in it is called the saturated zone. And the top of this is called the water table. And so if you think about like the top of the, let's even say this one, the top of this aquifer here is called the water table, and this entire little region right here. So let me actually draw it here. If we look from here until here, that is, here, let me erase this now. Uh, that is the saturated zone. And then this here, so saturated zone from here to here, and then the water table runs all the way across here. And see how it can flow into a lake as well. And so that's pretty important. Then we also have, usually it's made of impermeable clay, but we have these things called aquicludes, which are also called aquatards, and they stop water from flowing between them. And so this can confine the water above and below. And this is called a confined aquifer. So an aquiclude, so think about like include versus exclude. An aquiclude excludes the water from other places. Aqui aquiclude. And then it's also known as an aquitard or a confining layer. And so if you drill a well into one of these confined aquifers. This is called an artesian well. And so there's actually no need for pumping in order for the water to flow out of it because there's a lot of pressure in these confined aquifers. And usually, an unconfined aquifer gets charged or recharged uh, with water infiltrating through the soil. So we see here that it's saying that a lot of the pressure builds up from the water being confined in the two layers, whereas an unconfined aquifer just receives a bunch of new water easily infiltrating through the soil. Then we have surface water, which includes, as said before, lakes, ponds, streams, rivers, and constructed and natural reservoirs. So those are going to be human constructions. And we're only considering fresh water here, not the ocean, even though that's technically surface water as well. And some surface water is fed by groundwater, such as a spring is a stream that just springs up out of an aquifer during wet times of the year. And this is actually very vulnerable to contamination. So most pollutants are going to be found in surface water. So if that may be a complicated question on one of the tests where it asks which kind of water is most likely to be contaminated. Well, it's going to be surface water because there's little to no filtration, unlike groundwater. So groundwater has to go through the dirt through precipitation and such, whereas the surface water does not. So again, if we take a look at this chart here, we can see a flowing artesian well coming out of the confined aquifer or the artesian aquifer. And we can also see that there is a water table that runs across the top. A water table well just takes from the water table and it doesn't actually flow up on its own. Next up, let's talk about the transport of water. So we talked about the aqueducts, which were made in Rome, but usually still today we get a lot of our water from distant locations. And so this actually has to ensure a couple things: cleanliness and a long distance transport that is the cause of inadequate local supply. And so in grassland or desert environments, this actually creates some habitat fragmentation problems. So this is one of the first problems that we were introduced to in transporting water is fragmentation problems. So you may be asked a question about fragmentation and how water and aqueducts may influence this, just like when roads are built. And so here are a few of the effects, which are vegetation is disrupted, soil is disturbed, animal habitats are altered or destroyed. And so this here says that even if it's buried in an underground pipeline, this there's still disruption that occurs during the construction process itself. So you still have to go and dig under the ground in order to get an underground pipeline in there, and therefore you're disrupting the habitat. And so once these pipelines are constructed as well, they'll degrade over time. So one example of this is in Jordan and the occupied territories of Israel, we have as much as 55% of the water, which is carried through aqueducts, is actually lost because of leakage from old or damaged pipes. So remember that number 55% being lost here. Then we get into desalination. So desalination, think sal is salt. So we're removing salt from naturally salty water, which is usually seawater we're getting it from. So most of the places that make fresh water from desalination technology are the Middle East and North Africa. They make up more than 50% of the fresh water produced from this. And usually there are two methods to desalination, which are distillation and reverse osmosis. So, distillation, this is where you're evaporating water to boil it, make steam. The salt doesn't go with the steam, and so the steam is condensed and it yields pure water. And then the salt is left behind. And then in reverse osmosis, we actually have water forced through a thin membrane at a high pressure, and the water passing through will be really pure, but the water left behind is called brine. And so brine is extremely salty. And so we can remember that in reverse osmosis, the water is traveling from one end to another through a thin membrane at a high pressure, leaving brine behind and pure water on the other side, allowing for a greater, the brine will have a greater concentration of salt than seawater even does. And this can actually adversely impact local marine ecosystems if we pump back the brine into the sea. And the result of this is increasing salt content and depleting oxygen levels. Now we will discuss water use as a whole and how much water is actually being used. So, 334 million people are in the United States as of 2023. And we use a total 408 billion gallons of water, which is about 1,300 gallons per person per day. So remember those numbers, 408 billion gallons, which is a little more than the 334 million people in billions, except so multiply by 1,000, add a little bit of more to 408, and you'll get the billions of gallons of water per day, which is 1,300 gallons per person per day, which is a ton. And this includes pretty much all uses of water, direct and indirect, including domestic, inside and outside, and commercial and municipal use, irrigation, water for cooling and electric power plants. So pretty much everything you can think of in water, we use it for. So domestic, commercial, municipal, irrigation, electrical power plants. And then in the world, every other country pretty much uses way less, not way, but it is lower in other countries, water use as a whole. Now, if we look at world food production, 40% of food actually is irrigated. So we have 40% of food that all of the world is producing uses irrigation. And so about 1,000 tons of water, which is 250,000 gallons, is used to produce 1 ton of grain. So it's 1,000 to 1 if you're looking at a ratio here. Or, well, yes, 1,000 to 1 for tons, and then 250,000 gallons is the volume that we see, whereas tons is the weight. So if we take a look at how is irrigation happening, actually a large amount of the water in irrigation actually is lost because of evaporation. And a lot of the time, irrigation and conventional irrigation here, water runs through a ditch alongside a row of crops. So there's this water stream that runs just right alongside the water or the crops. And this is only 60% efficient. So this is conventional irrigation. So think about efficiency. Well, a large fraction is lost to evaporation. So that's why it's only 60% efficient here. Then we have drip irrigation, which actually can be up to 95%, which is very efficient, probably the most efficient. And there's a tube that you bury under the ground, and then it releases the water very slowly. But this is very expensive. So a lot of farmers can't really afford this because they're already trying to make a living off of the crops that they make. Then we have livestock and fish farming, which are actually relatively small consumers of water. Well, no. Yes. Livestock, fish farming, mining, and industry are all relatively small consumers of water in the United States. And so we can remember livestock, fish farming, mining, industry as not taking up too much water. Because if you think about it, livestock, they just need to drink a normal amount of water, whereas plants need to be like watered constantly. And then fish farming, we have where they're already in a lot of areas with water, so adding water is not too much needed, but it is needed. Mining, we use a little bit of water, and industry, we do use a little bit of water for that. Think about like cooling of power. Then this also notes that a lot of the water that we use in all categories really has not changed much in the last 2 decades. So we haven't gone up, we haven't gone down. So it might ask, what is the state of water use changed over the past 2 decades? It'll say a little bit, 2 times more, 2 times less, or a little bit less, or no change. And the answer is no change. Now, ultimately, water impounded for hydroelectricity. So if we think about water being stopped from flowing in order to generate hydroelectricity, this is not included in geological surveys use categories because it's not being used. It's just ultimately being withheld and then eventually poured back into the same location it would have before impoundment, which is this withholding of water. And therefore, it's not used up in this way. So then we start to get to these ideas of, well, how do water shortages happen? And a lot of this is drought. So this is an extended period of limited precipitation. So this is either used because of natural climate change or human activity. And this often of disastrous proportions. This often creates disaster in several places. And so there is currently a drought in the Horn of Africa, which has impacted Ethiopia, Kenya, Sudan, and other East African countries since 2020. And this has affected in this area human life, livestock, and other long-term effects on the land. So we talked a bit about drought when we were discussing soil and how it may not have the ability to produce new layers of soil or support agricultural use when you have low water amounts. So it then begins to talk about how prolonged droughts, so time, remember, is one of those state variables for soil, will actually cause the topsoil, O and A horizons, to desiccate and blow away. So we have that destruction of the soil on the top and it blows away. And so a lot of agriculture can't then use this soil anymore. And so agriculture will be degraded because of the degradation of the soil. And so we also see that erosion from flooding happens more when there's heavy rain after drought happens. And so the soil can't absorb a lot of water because it's so dry. And so the land is very parched then, even when it's raining and flooding. Now, still, aquifers do contain water even in long droughts, but if they're heavily pumped during these dry periods, then we can see that aquifers are depleted. And so if output exceeds input, then the water supply may be depleted in these aquifers. And so sections can be overpumped, and this leads to local shortages, especially manifested by one or more wells going dry. So wells can just completely dry up in droughts, especially if they're overpumped. And so now, what is the cause of this overpumping? Well, it's irrigation. So you may be asked, what is one of the causes of uh, overpumping of aquifers in many countries, which is that answer would be irrigation. And so the most well-known case of this is in the Ogallala aquifer, which ranges from Texas and New Mexico to South Dakota. So Texas, New Mexico, all the way to South Dakota. And a lot of this overpumping can result in a reduction of water quality overall. And so if you overpump, think about you're going to have less water in there. So if, say, there's a coastline nearby, then maybe salt water will be drawn in because less fresh water is in the pump or in the aquifer. And so more water will be able to come in that's not so good, maybe salt water. And so then this is called saltwater intrusion. And this is actually common in coastal areas because we take out so much water from the aquifers and so much salt water comes in. Finally, we get to talk, before water pollution, we get to talk about floods. And so these can be devastating because, uh, especially in places where home construction isn't strong, we can see that also there's places where there's not very good transportation to get people out of areas of floods. And so this is where they're most devastating, is when there's not good home construction and there's not good transportation. So in West Bengal, India, uh, in 2000, in the year 2000, it destroyed more than 800,000 homes and killed hundreds of people. This is all because the homes were not constructed strong enough. This flood destroyed them and it killed hundreds of people because the transportation wasn't enough to get them out of the area. Then in 2023, there's even more flooding. So this can be driven by intense storms, such as from Pakistan to New England. So a bunch of different places around the world have storms, is all that's saying. And water management actually uses lots of systems, such as canals and levees, to bring water in flood-prone areas around to other places in order to transport water and take advantage of these floods rather than let them destroy people. Now, floods, hurricanes, and torrential rains, so all these storm-related stuff, actually can have environmental benefits of how water flooding banks, such as rivers or lakes, can actually uh, transport nutrient-rich sediment, which improves the soil quality in the adjacent areas. So think about those riverbeds. If water is able to flow into those riverbeds more, then the nutrient-rich sediment is able to move into areas around those rivers. And so that was a lot of water. And next up, we're going to begin talking about water pollution as a whole and how we manage it. So, yeah. Okay, so next up, we're going to be talking about water pollution itself. So, we see where water is consumed from, which is from rivers, streams, and dug wells. And sometimes this same water, it's the supply for drinking, bathing, washing, cooking, and the disposal of human waste. So, these are the main uses of water that we use it for. But this water can be polluted and actually can be a source of infectious diseases. So 1 to 2 billion, between 1 and 2 billion people actually don't have access to safe drinking water, meaning it's polluted for 1 to 2 billion people on Earth. So a lot of these people are actually in the developing world. And also, bodies of water can be degraded that can cause significant damage to the environment. So if water is degraded, then the environment itself will also be degraded. And so if we then take a look at figure 65, there's a lot of different pollutants. So if we look at this figure and we can study it here, we have percent of impaired river miles is going to be the purple here. And then assessed river miles that have been checked in each of these sections. So they're probably mostly going to test on, okay, what's the most or the least of all of these? So we'd want maybe they'd give us even options of just siltation, habitat alterations, oxygen depleting substances, and nutrients, and we'd need to know what's the most or what's the worst. So memorizing this chart going all the way down is pretty important. So knowing that the leading pollutant is bacteria or pathogens, then we have siltation. So actually, soil itself is second highest when it comes to pollutants. And then we have habitat alterations, which are next up. And we can also remember it goes from 35 to 10%, so that can help us estimate if we're ever guessing. And then we have oxygen depleting substances. So we'll talk about later on, we'll talk about BOD and uh, different, well, as it says here, oxygen depleting substances. And then we have nutrients and thermal modifications and metals and flow alterations. So habitat alterations is third. That's actually connected to soil, so you can think of it as pathogens, obviously, is going to be very polluting. And then we have um, siltation is next up. You can remember that. But then remember, siltation leads to habitat alterations, like in our minds, it can lead to it. And then with those habitat alterations can come oxygen depleting substances. In the midst of oxygen depleting substance, there is some good that we must remember, and that is nutrients. And now that's not absolutely good for the water, but it is a pollutant still. But in our memorization, we can remember, oh, it takes a better turn in the later half. Then we have thermal modifications, which is just a complete turnaround from the nutrients themselves. So then we get metals, which are connected to thermal because metals heat up, I guess. This is how I'm connecting them for memorization purposes. And then metals to flow alterations. Well, electricity flows through metals in flow alterations, and flow alterations will be the least. Okay, so next up, we're going to be talking about non-point sources and sources and point sources. So point sources, they have confined locations such as a factory or pipe leading from a sewage treatment plant, or non-point sources, which are like entire regions, such as like a farm or farming region, a suburban community with lots of lawns and septic systems, or runoff from parking lots. So these general areas are actually harder to control. So if the bulk of the waterway pollution is coming from one or two point sources, then we can target those sources. Point sources are specific, so we know what to fix. So we go and fix those, and we can actually control them versus non-point sources are difficult to control. Then we have types of water pollutants, and so we're going to start by talking about disease-causing organisms such as pathogens, so parasites, bacteria, and viruses. These comprise pathogens. So in this sort of a question, they might ask like, which of the following is are all pathogens, and then they'll list different things. So parasites, bacteria, and viruses. And this can, if they contact the water or ingest the water, then people can get those diseases. And these are relatively rare in the US, but do occur occasionally. So, how often do large-scale disease outbreaks from municipal water systems happen in the United States? Well, occasionally. Now, they are relatively common, however, in the developing world. Now, pathogens can come from both point and non-point sources. So, for example, sewage treatment plant or septic system means pathogens going into rivers or lakes. Wildlife can also contaminate those reservoirs with disease-causing organisms. So, wildlife that has the disease can go into the reservoirs and therefore bring the disease into the reservoirs. So some of the major waterborne diseases are cholera and hepatitis. So if you may be tested on, okay, which diseases are waterborne, it's cholera and hepatitis. So uh, cholera happens more in developing countries, thousands of lives, versus hepatitis A is actually happening more commonly in the United States because of unclean restaurants, more specifically. So If you have unclean restaurants, then that means hepatitis A is going to be coming for you. Then there's cryptosporidium, and this is a gastrointestinal illness, which actually we also have. Okay, so it doesn't say anything else about cryptosporidium, but it just says that it's a gastrointestinal illness. But Giardia is actually from mountain rivers, which many hikers think is pure enough to drink from, when in reality it's not because it can have this Giardia. So if I imagine Giardia, I think of like a guardian as they walk through the hiking site. And so if you're ever asked about what is Giardia, where do you get it? Well, it's like a guardian, Giardia, and it's guarding them on the hike, except it's not. It's actually there to kill them. That would be terrible. Oh my goodness. And then we have, so how do we remember bacterium, the cryptosporidium, that it's a gastrointestinal illness? Well, gastrointestinal is a very fancy term there. And if we remember, well, gastrointestinal is a fancy term. Crypto is a fancy type of money. So if we put the two together, and spore, gastrointestinal, like spore, like a mushroom, like it's spore, it's a mushroom spore. But alas, we can remember that. Then we have oxygen demanding waste. So this is material that includes organic matter, so like leaves and twigs, and this will decompose. Bacteria grows on it, and it uses oxygen to survive. So if leaves and twigs are left into the river, bacteria grows on them. And then those bacteria will start eating up the oxygen that's in the water, which will deplete the available oxygen. And so some of the oxygen demanding wastes that these include are food scraps, human waste, and animal waste. So something really important, you may be asked, like, if you drop a bunch of food scraps into a river and or if you drop a bunch of food scraps into a river, how does it become oxygen demanding? And so you need to know that it will decompose and that bacteria will grow on which uses that oxygen in order to survive. Now, what is oxygen demanding waste measured in? Well, it's measured in biochemical oxygen demand, or BOD. And so this is the amount of oxygen a defined quantity of water uses up over a period of time. So how much oxygen is being used up in that water, or how much the water is using up the oxygen. And usually it's over a period of 5 days. We usually measure it in 5 days, and usually at a specific temperature. So usually 20 degrees. So you may be asked, well, at what specified period of time is BOD usually measured? 5 days. At how many degrees centigrade? 20. Now, if we have lower BOD, then that means it's less polluted because less oxygen demanding waste is inside of it and less bacteria is growing on those different waste matters. Now, if we have higher BOD, then we have more oxygen demanding material. But if there's no organic material in the water, the bacteria occurring there won't have anything to feed on. So the substrate is just something to feed on. And so it won't survive and use oxygen. So it won't be eating up that oxygen. And if we're measuring specific oxygen demanding waste, such as domestic sewage, it might have about 200 milligrams of BOD per liter of water over 5 days. So it's measured in an amount per an amount of water over 5 days. And so natural water usually has 5 to 20, and these usually come from leaves, twigs, and dead organisms. So if we're looking at, for example, rivers and streams, it'll usually have about 5 to 20 milligrams per liter over 5 days versus sewage is 200, which is a lot more, which means there's a lot more bacteria in it. Then we can see how much dissolved oxygen is actually in the water. And so this can be measured in parts per million, so ppm, just like just like carbon dioxide in the atmosphere. And so, when dissolved oxygen is high, BOD is low, which makes sense because uh, if we have our biochemical oxygen demand high, then that means less oxygen is going to be there because there's more demand for the oxygen there. Versus if it's low, then that means the dissolved oxygen is high. Now, in high quality water, there's about 8 to 9 ppm, so almost 10, but not quite there. And then polluted environments has 4 ppm. So now I'm gonna quiz on a couple key points. So if we really quick take a look at a bunch of these things, we're gonna quiz on how about how how many days is the BOD measured in? It's 5 days. What temperature? 20 degrees centigrade. And then what is the order of pollutants that make up most river miles? It's going to be, for most, it's going to be pathogens slash bacteria. And then we at the very bottom have uh, flow alterations. Yes, flow alterations. So then we need to remember that the next one is siltation, habitat alterations, oxygen depleting substances, nutrients, thermal modifications, and metals. So keep going back over these things so that we can remember them later. And then also let's quiz on in normal water, what is the parts per million of dissolved oxygen? It's 8 to 9 ppm. And in polluted water, 4 ppm. And let's continue forward for there. So remember, 200 milligrams of BOD per liter per water is over 5 days for domestic sewage. And then natural water is 5 to 20 BOD. Okay. Figure 66 here shows different sources and non-point sources. So if you understand the ideas of these, then we should be okay. Next up, we're going to look at figure 67 and how dissolved oxygen and BOD interact. So sewage is falling into the water, and so phytoplankton bloom thrives on those nutrients of the sewage, and so dissolved oxygen is being used by the phytoplankton, and so the dissolved oxygen is trapped in the lighter layer, and then this causes lighter freshwater and heavier seawater, where we have uh, dissolved oxygen is being used up by the microorganisms in respiration, and this leads to hypoxia, which is the absence of oxygen, and the nutrients that the uh, dissolved oxygen is being used up by the microorganisms that are feeding on the nutrients, and this is causing the oxygen to be used up. And then there are some fish that are able to avoid hypoxia. And with the decomposition of organic matter means that more bacteria is going to be growing or more even phytoplankton going to be using up from biochemical oxygen demand. And then we have shellfish who are unable to escape hypoxia. So remember that may be tested on like which organism is unable to escape hypoxia. That's shellfish versus fish are able to avoid it. Then we should get into pollutants that are inorganic, or those that come from animals or plants. And so we actually discuss these in nutrient cycles in section 2. And two that are most likely to limit growth are nitrogen and phosphorus here. And if too much nitrogen and phosphorus are present, they overfeed the body of water. So this means nitrogen, phosphorus give nutrients to algae and create an excessive growth of algae. And this is eutrophication, which is an oversupply of nutrients. Um, or the eutrophication is the excessive growth of algae because of an oversupply of nutrients. And we actually discussed this way, way up here, all the way if we go back here to Mono Lake. So if we looked at Mono Lake here, we can see that because of the algae overgrowing, let's see, where is it? So with a slower nitrogen uptake, this means that the uh, algae population has less food. So it's the opposite of eutrophication. And so then the flies and shrimp were less because they were feeding on less algae because the algae could take up nitrogen less in relation to salinity. So if you have less or greater salinity means slower uptake of nitrogen, which is what we're talking about here, which can slow the growth of algae population, which means less food for other organisms. So that's an example here of where, let's find it, of where non-chemical or non-organic inorganic compounds can affect the lives of organisms. So if algae grow too much, then they die and decompose, then the BOD increases, and then the fish population declines. And so uh, where does this nitrogen come from? Well, it comes from farm runoff, sewage treatment plants, acid precipitation. So if we're thinking, okay, farm runoff, that makes sense. That's from like fertilizers. Sewage treatment plants, this is from, well, sewage. Nitrogen is going to be present in sewage because it's present in waste. And then we have acid precipitation, so acid rain, nitric acid. And then phosphorus actually occurs naturally in rocks and minerals, fertilizers, once again, fertilizer runoff. And in the past, detergents used to contain phosphorus as well. So remember that detergents have some phosphorus in them. And then some other inorganic pollutants include acid precipitation, which is nitrate and sulfate, remember? And then point sources such as byproducts of sewage treatment, so like chloride and metals. So chloride and metals are um, inorganic pollutants once again. And if you remember, chloride is the one that they forgot to write in for micronutrients or nutrients that plants and organisms need as a whole in order to survive, but in little amounts. And they accidentally replaced it with the word cobalt, and it should have been chloride. Then we have metals, which are industrial plants give off metals. So, like lead, copper, arsenic, and mercury. So, these are the most toxic water pollutants. So, which of the following is the least toxic? They'll probably ask, and they'll ask lead, copper, arsenic, mercury, and say they say iron as well. You need to make sure to say, okay, lead is definitely toxic, copper is toxic, arsenic is very toxic, so is mercury. So we can wither it down. So if you know how toxic these things are, copper is toxic, you may not realize. Just pure copper, it can be toxic. And so mercury actually in the early 2000s received a great deal of attention as inorganic water contaminant of global proportions. And so 2002 UN report said that It's created a lot of adverse impacts on human health. So this can actually happen from the consumption of fish, occupational and household uses, dental amalgams, and mercury-containing vaccines. So some vaccines contain mercury at the time, and then so did fish and occupational and household uses, as well as dental amalgams. So if you remember, we can think of like, oh, metal going into your mouth for dental work. Okay, that could have been mercury at one point in the early 2000s at least. And then we had consumption of fish. That makes sense because mercury will have polluted the water. Occupational household uses, that's just water in the house that's mercury hits there. And then the vaccines, apparently. There's a conspiracy, maybe. Like I could imagine people creating a conspiracy of, no making vaccines because they have mercury in them, when in reality, there were only probably a very select few that had mercury in them. Now, what is the largest source of mercury emissions? Coal and oil-fired electric power plants. What a surprise. Mercury comes from coal and oil, at least in the United States. And so, what does coal and oil give off? It's mercury emissions. Woohoo! Okay, so inorganic mercury, just Hg alone, isn't harmful, but when it go disperses through the environment, it becomes harmful. So, for example, in anaerobic environments such as wetlands, aquatic sediments, and temporarily saturated soils. So, saturated soils, that just means there's going to be organisms in them. Bacteria are able to convert this inorganic mercury into methyl mercury, which is very toxic. So, methyl mercury is what you're going to look out for. So, inorganic mercury, not too harmful. Methyl mercury, nah, we don't like it. Very bad. And so, this is very toxic to human beings. So, then, if we take a look, that what does methylmercury do? Well, it harms the central nervous system, such as coordination, sense of touch, taste, and sight, specifically in embryos and children. So embryos and children are particularly vulnerable to methylmercury. Persistent organic pollutants, or POPs, are toxic chemicals which persist in the environment decades longer and so can accumulate in organisms, such as humans, through food webs. So what that's saying, food webs carry different, well, foods through them. And so if a toxic chemical stays in the environment a long time, then organisms are more likely to take them up and therefore pass them on along the food chain up to us humans. And so one specific persistent organic pollutant here is polychlorinated biphenyls, or PCBs, which are highly toxic and carcinogenic. So carcinogenic means cancer forming, and they're highly toxic. So these were at one point used in manufacturing plastics and insulating electrical transformers until 1979. So question, until what year were PCBs used in insulating electrical transformers? Well, 1979. But we need to remember this date because what if there's a question on it? But another very important thing to note is that it's used in manufacturing plastics and insulating those electrical transformers. So plant plastics and transformers use PCBs, which cause cancer and are toxic. Now I want to go back just to review to stimulate our brains real quick while we're in the mood of memorization. If we look at, where is it? Here it is. Cryptosporidium. Remember the connection we created here? It's fancy, so it's gastrointestinal illness. And then Giardia is the guard of the hikes, of the hikers, except they really turn on them. Cholera is common in developing countries, and hepatitis A is in unclean restaurants. So I don't know why I was reminded of that, but might as well start to think about that. So because of their persistence, and even though PCBs aren't actually manufactured anymore in the United States, they are still persistent in the environment. They stay there, persistent organic pollutants. And so they're still present in the environment because they were at one point used, and now they just stay in the environment because they stay there. And so, um, let's see. A General Electric plant in New York State. So General Electric had at one point been a point source of PCBs into the Hudson River. So the Hudson River is in New York State, where a General Electric plant was, and they used PCBs. In 2002, General Electric then had to pay, according to the EPA, for the dredging and removal of about 2.65 million cubic yards of PCB contaminated sediment along 40 miles of the Hudson River. So 2.65 million cubic yards of PCB contaminated. That's a whole lot that they contaminated. And it's over 40 miles of the Hudson River. And so then in 2006, there was a legal agreement between the two, the EPA and the General Electric. And so it started in 2009. So the process actually took 7 years to go all the way through. And then it was completed in 2015. So not only that, we had 2002 all the way to 2015, 13 years of working to remove the PCB contaminated sediment overall, because it's 2002, 2006, 2009, and then 2015. Now, EPA actually monitors the river for those PCBs. Okay, so next up, we have non-chemical pollutants. So these, although they are not organic, so inorganic compounds, and these are organic, they are still chemicals. But if we're talking about pollutants that aren't chemical, then we can talk about sand, silt, and clay, which are another source of this water pollution. So we're thinking about, okay, well, even soils can be pollutants. Now, how? Well, housing and shopping center development and road construction, so buildings and roads, and agriculture. So we're using the soil and it may be degraded, remember, and blown away in the wind and deposition happens. These are all major sources of sediment. So the sediments settle out of the unmoving water, and uh, this is when a dam is constructed as well. And so if it's remobilized, then so if the water keeps moving even after it's unmoving, then a lot of the sediment will end up in the downstream river water. And the negative effects of this is clogging fish gills, hinder fish from obtaining oxygen, especially oysters and clams, so bottom dwellers. So this, so if you're thinking about down here, shellfish are very similar in this way to oysters and clams. And then if we increase sediment in the water, uh, then this will actually reduce the infiltration of sunlight. Think about sunlight, it's going to be harder to hit the bottom if there's a bunch of sediment all making the water all murky. And so this actually reduces the productivity of aquatic plants as well. So anything that's trying to get that sunlight, well, it's not gonna get sun. So next up, if water moves more slowly, or it receives more sunlight, or enters a shallower waterway, then that water has temperature that's going to increase. So these are all ways which water temperature increases. And it can also be heated for cooling in industrial processes and electricity generation. so like fossil fuel fired and nuclear power plants. So this is called thermal pollution. So if we thermally pollute the water, the problem here goes back to oxygen again. It actually reduces the amount of oxygen that's dissolved, that can be dissolved in the water. Now, water organisms still have the same respiration rate, which means they'll use more, it will actually increase their respiration rate in warmer waters, which means they're using more oxygen and there's less oxygen in the first place inside of the water. And so it's reducing this dissolved oxygen in the water. And this means that they have less oxygen to take in overall. And so their increased respiration rate can also be a stress that makes them more susceptible to disease. So higher temperatures mean lower amounts of oxygen and increased respiration rates, and therefore stress that causes disease. So if we were to go ahead and draw this here, we go from uh, temperature goes up, then we have comma, we have that means oxygen or dissolved oxygen, DO, goes down, and then we have respiration rate, R, goes up, and these two kind of go together, right? And then because of this, we have stress, increased stress, and therefore increased disease. Okay, so hopefully that helps you remember. And next up, we're going to talk about ocean and shoreline pollution. So if we take a look at, okay, we've taken a look at freshwater a lot, but now we need to look at shorelines. So some of the biggest ones are crude oil and other petroleum, which can be toxic to, which are highly toxic to marine organisms such as birds, mammals, and fish, as well as algae and microorganisms that are the base of the aquatic food chain. Now, it's persistent, so then it stays in the water, and this spreads for hundreds of miles, leaving a thick, viscous covering on land that is extremely difficult to remove. So it's hard to remove oil from, well, water because it's very separate, or even just hard to remove in general from areas because water and oil do not mix. And so this will harm a lot of birds, mammals, fish, all of these, and microorganisms. Then, how do this oil and petroleum end up in the oceans? Well, it happens from spills from offshore drilling and oil tankers, and the most notorious of this was Deepwater Horizon oil spill in 2010 in the Gulf of Mexico. So this was the most notorious one is Deepwater Horizon oil spill. This was when the last, or not the last, but one of the biggest in the Gulf of Mexico. 210, so we can remember 2010 and 210 million gallons of oil covered a bunch of miles of ocean. So remember, this can cover, it said, uh, hundreds of miles, leaving thick, viscous covering. And this was covering miles of ocean and coastline, which actually impacted one of the most productive marine ecosystems on Earth. So, this is referring to the Gulf of Mexico. And so, still cleanup efforts are happening. And so, how do we actually clean them up? Well, floating booms to keep a spill from spreading, uh, skimming oil from the water's surface, and chemical dispersants that break down the oil into particles that can be broken down by sunlight and bacteria. So chemical dispersants can really help in this way of breaking down the oil so that those organisms can then further break them down and just get rid of them out of the environment. And so then we get into solid waste pollution. So Solid waste in open waters has been reduced since the 1980s. Now, I want to test 1975 was a certain year that we talked about earlier. What was happening in that year? Well, if we go back here. Oh, let's see. Or 79 maybe? Was it 79? Yes, 1979. Plastics and insulating electrical transformers used PCBs until 1979. Okay, so back to this. Reduced since the early 1980s. We can still, however, find bottle cigarette butts and food packages, which are all solid waste, all because of negligent people and open landfills, and these travel long distances and end up washed on another beach from where they started. So it's not only unsightly, but it can be dangerous to the marine organisms and people. So this is standard stuff. Like when you think of water pollution, you don't just think of oil, you don't just think of chemicals, you also think of solid waste, all the plastic that can be inside of water. So these can actually pose a threat to children and such as beverage six packs and plastic bags that are strange to many animals, and so this can hurt them. Now, plastic debris in landfills or water bodies can actually degrade over time and make microplastics, which are particles smaller than 5 millimeters. So I've had a question before where it asks, microplastics are best described as what? And that is particles smaller than 5 millimeters. And then nanoplastics are smaller than 0.0001 millimeters. So nano, oh, uh, now I gotta scroll all the way up. Nano versus microplastics are different because it's less than 5 millimeters versus less than 0.0001 millimeters. And so they've been found to be a potential health risk for animals and humans who can eat them from contaminated seafood as well as other sources. Then we have where we're talking about, well, let's review this one more time. Contaminated seafood can have these microplastics inside of them and therefore contaminate animals and humans and be a health risk. So next, we need to talk about wastewater treatment. So wastewater is all the water from houses and buildings, which uh, goes to a sewage treatment plant or septic system. So these are two different ways of filtering wastewater is sewage treatment plant and septic system. And this is wastewater is actually very highly varied. So wastewater from toilets can be harmful and then needs to be treated before return to the environment. But if it's from a sink or a shower, then it can be less harmful to the environment, even though it does have some BOD food components, so uh, biochemical oxygen demanding food components here, and some inorganic contaminants, such as like from soaps and detergents. They're less harmful overall than what waste from toilets will be. Then wastewater from toilets sources other than toilets is called gray water. So we talked about gray water earlier with Julius Sextus Frontus. And he was the first, possibly the first, to ever suggest that we should use gray water for other things and separate it out of the aqueducts, if you remember. And so this is sometimes even introduced into the environment for things like watering lawns. And so If we're looking at human sewage as a whole, it's high BOD material, and sewage we're talking about from toilets. So we have high BOD material that can contain pathogenic organisms, that just means harmful organisms, with high levels of phosphate, nitrate, and other compounds. Remember, we talked about non-organic compounds. Phosphate and nitrate are harmful to the environment because they are can then create algal blooms in eutrophication. And so raw sewage dumped from a free into a free flowing river be uh, would not be good for raw sewage. But then if it's treated or naturally or passed through a human-made system, uh, we usually have to dump it into the river after it's treated in naturally or human-made systems. So we can also see a solar aquatic system. These things will be broken down. So the basic idea is the same. Bacteria breaks down the organic matter into carbon dioxide and inorganic compounds like nitrate and phosphate. Then the dissolved oxygen levels of the water are reduced, and eventually BOD goes down. Then the oxygen levels recover. So wastewater treatment facilities actually use this natural process of bacteria, they break it down, make it into carbon dioxide and inorganic compounds. Then the dissolved oxygen levels reduce because of that biochemical oxygen demand. But then the BOD goes down because the dissolved oxygen levels in the water go down. And so uh, then the oxygen levels are able to recover, and we use this in order to decompose the sewage itself and allow it to be treated from this BOD and the oxygen demanding waste. And so usually we have different methods of treatment here. So we're going to go ahead and describe the process of treating water. So this has got to be used by most municipalities in developed countries. And so it's actually accomplished in two phases. So there's primary and secondary treatment. The primary treatment removes 40 to 50% of the solid waste material. So solid waste that's in the sewage, 40 to 50% of it is removed in primary treatment. Then this solid material is settled out during the process and is eventually dried out and classified as sludge. So this 40 to 50% of solid waste, it's classified as sludge in this primary treatment. And so this usually contains a lot of metals, especially if it's coming from industrial businesses. So if we have a lot of sewage that is coming from industrial businesses, then we're going to have a lot of metal inside of the sludge. Then, after you remove the sludge, the water undergoes secondary treatment, which breaks down the organic matter as if it were to decompose naturally. So, after this secondary treatment, 85 to 90% of the original pollutants have been removed. Then, the water is disinfected to kill pathogens and then returned to the river and lake to become part of the water cycle. So, if we look at figure 68 here, we see in primary treatment, we see raw sewage going through screens, a communicator, a grit chamber, and grit disposal, and primary clarifier, flowing the primary effluent out, and raw or primary sludge going out through the primary clarifier to sludge treatment and disposal. And then we get to secondary treatment, in which we have an aeration tank, and we are giving then air to those bacteria and such in order to leave the sewage to decompose naturally in a way. Then it goes through a secondary clarifier, which gets rid of more sludge, and it then returns the sludge back to the aeration tank until it is heavy enough to go back through sludge treatment and disposal. And eventually, secondary effluent goes out through a disinfectant and it has discharge to surface water, and sometimes it can have tertiary treatment. So try and remember this chart that it goes through raw sewage screens, communicator, grit chamber, grit disposal, then the primary clarifier and sludge, then secondary treatment happens where we have an aeration tank. Sludge goes in a system throughout, returning and going until it can leave through the secondary clarifier, and eventually disinfectant is added. So, how have we been able to improve water quality in the US? Now, in the past few decades, we've actually been able to improve the water quality overall. As we saw, if we go back up to here, since the 1980s, we've had solid waste dumping into open waters has been reduced since the 1980s. This has been the past few decades, so 40 to 50 years ago, a lot of harbors and waterways were badly polluted. So thinking 1970s and 80s. Then the Clean Water Act was passed in 1972, and it was actually amended a lot. Then the Safe Drinking Water Act of 1986, and the Water Resources Development Acts in 1986 to 92. So a lot of these are happening in the 70s, 80s, and 90s. And these all worked to protect surface water by managing the water supply, wastewater, food control, navigation on waterways, and hydroelectric power. So water supply, wastewater, flood control, navigation on waterways, and hydroelectric power. So what we're getting our water from, the wastewater we have, flood control overall. So how are we controlling the rainwater that overaccumulates? And then navigation on waterways and hydroelectric power. And so these are all different uses of water. And the Clean Water Act requires that water quality standards place an upper limit on the concentration of specific pollutants. So there's water quality standards, which have specific pollutants limited to the amount that they can be in major water bodies. And so that's what the Clean Water Act outlines. And so we aren't going to talk very much. We're going to talk later about the Safe Water Act, but we aren't going to just also talk about Water Resources Development Acts. These all have worked together, though. And so, in order to carry out the Clean Water Act, there has been a total maximum daily load which each pollutant can have. And so this is the max amount a pollutant can enter a water body in. So this is an upper limit on the concentration of specific pollutants. That's what the total maximum daily load is. And so it's based on the amount of pollution discharged from point sources such as factories and wastewater treatment facilities and etc., and non-point sources, so atmospheric deposition, farms, other runoff, and so forth. So these are regulated to the best they can. So we can think of these as a maximum size, the pool of each pollutant in the system. So yeah, we can think of the max size as this pool of pollutants that's inside of the water. These are the maximum allowable inputs, the total maximum daily loads are. And so here we have a chart that outlines what is the total maximum daily load calculated by. Well, it's calculated by point sources plus non-point sources plus natural background. So that's waste load allocation is the current and future point sources. So those point sources in the waste load is known as waste load allocation. And then load allocation is non-point sources and natural background. So waste load is point, load is non-point. So think about the word waste is present in waste load allocation, therefore it is a point, versus waste is not present in the word load allocation. So it's non-point, it's not there. That's how you can memorize that. Then we have a margin of safety, which we don't know the pollution load and environmental/health impacts exactly. So we need to create this margin here. that is to say the safety of certain pollutants and say, okay, do we need to raise the total maximum daily load or do we need to lower it? Now, in the Safe Water Drinking Act, the EPA, the Environmental Protection Agency, actually established the Safe Water Drinking Act. So this is not the Clean Water Act, this is the Safe Water Drinking Act, specifically for drinking water. This established maximum contaminant levels. So this is different from maximum daily loads. And so this is just a different version almost. And this is for 77 different elements or substances found in municipal drinking water sources. So in the water that we drink, there are 77 different elements that have a maximum contaminant level that we cannot exceed. Now, the word enforceable is very important because the EPA cannot enforce all contaminants to be removed because there's bound to be some pollutants at least. And so the MCL reflects the concentration in which the harm is thought to occur and the feasibility. So feasibility is that enforceability of achieving a standard based on the existing technology to treat the water to attain such a level. So notice it was 85 to 90% effective in removing the original pollutants after secondary treatment. Notice that's 85 to 90%, not 100%. And that's because we have limited technology. And so, while water regulations have greatly reduced contamination of waters and have almost eliminated, so we've almost eliminated all major point sources, non-point sources are much harder to be controlled. From oil from parking lots and nutrients from suburban laws are two very hard to control regulations. And so that's the end of the water video in which I discussed water as a whole, water resources in science section 3. And so I would like to give you your next word for your sentence. And that word is the word is. So far you should be forming a sentence and we will see how it goes in the next video. Thank you for watching.